the first thing we do is to draw a sketch. In step 1, we draw a sketch. We use the sketch to understand the problem, to understand the meaning of the question. Okay. Draw a sketch. So this one is simple. You are trying to make a box using a square. You know the size of the square, 12 by 12 inches, right? Now we are on step 1. So can you write out 1? You draw a sketch. You draw a square. Try to label the size of the square. The size of the square, the dimension. I think most people call it dimension. Okay, but it's not the real dimension if you are in linear algebra. So they're different. In daily life, in real life, so people just call it dimension. The dimension is 12 by 12 inches, right? So you have the width. So basically, you have a square. The width and the length are the same, 12 by 12 inches. Okay. Try to follow me and understand the problems. Okay. And then you want to cut off. You want to cut off a small square at all the 4 corners. So now let's say you cut off 1 square, 4 squares at the 4 corners. Okay. You cut off the small squares at all the corners, so that you can make a box, an open box. I think the problem is trying to ask us to make an open box, right? An open box, so there's no top. Try to understand the meaning of the problem. After cutting off the 4 corners, cutting off the 4 small squares at the 4 corners, and then you can fold up to make a box. If it's a real face-to-face class, I could use a piece of paper to show you, but now you should imagine. Okay, after cutting off, you fold up. You fold up that portion, that portion, that portion, and that portion to make a box. You know what I mean, right? Okay, now let me try to ask you a question. As long as you can answer the following question, then you know you're following me. You know what's going on. Okay. Actually, we do not know the size. The dimension of the small squares to cut off. At this point, you could cut off any size, as long as you could make a box. But if I'm going to use x to denote the side length of the small squares, I want to repeat, if I'm using x to denote the side length of the small squares on the 4 corners. So what is the height of the resulting box? I want to repeat my question. What is the height of the resulting open box, if the side length of the corner squares I'm going to cut off is x? What is going to be the height of the small squares? What is the height of the box? Yeah, 12. So 12 minus 2x is it's going to be the base, the side length of the base. I was asking for the side. Yeah, for the height. As long as you know that, and then I believe you're following me. Okay, you know what's going on. So I'm going to. Okay. So basically, after cutting off the 4 corners, you are going to have a shape something like this. So something like this, right? And then you fold up the 4 portions. So now let's say, so that's portion 1. So that's the plane region 1. That's the plane region 2, right? That's the plane region 3. That's the plane region 4. You fold up the 4 portions, and then you can have a box, an open box. I think the meaning is clear now. Okay, so that's the problem. That's the problem. Okay, actually, the actual problem is what is the size of the corner squares you want to cut off to make the resulting box has the largest possible volume. We want to maximize the volume. So do you see the problem? So what size of the corner squares should be cut from each corner to produce the box with the largest possible volume? So that is the problem. Okay. Now let's try to understand the problem a little better. Okay. And the volume is not going to be the largest if the corner squares are too tiny. So do you know what I mean? If the corner squares are too tiny, then the resulting box, the base is going to be bigger, but the height is going to be tiny. The height is going to be tiny. Okay. So the resulting box is going to be very flat, very flat if the corner squares are tiny. You can imagine the volume is not going to be the largest. All right. On the other hand, if it's possible to cut off some larger corner squares, so later on, so we're going to talk about what is the largest possible one. I mean the largest possible size of the corner squares you can cut off. But you imagine if you cut off very big, as large as possible, I mean corner squares, then the resulting box is going to be very tall and very slim. So can I use the wording slim? I mean, I believe you can imagine that. But if it's very tall and very slim, then the resulting volume is not going to be the largest either. So because it's too thin, right? Now here comes the actual problem. So what is the proper size of the corner squares you want to cut off so that the resulting volume is the largest? So do you see the problem already? Okay, draw a sketch to understand the problem. And then in step 2, in step 2 we make a list of variables. So by that I mean for each quantity you identify the quantities we need, and then you make a list of variables. I will tell you how. Okay. So first of all, to make up a list of the variables, identify the quantity for which you want to maximize. Anybody want to tell me for what quantity we want to maximize? The first thing you do is to identify the quantity you want to maximize. For what quantity we want to maximize? Volume. Okay. Use a notation to denote the volume. We want to maximize the volume, right? At least we need one variable to denote the volume. Okay. So let V be the volume. We kind of use the standard notation. You know V is the standard notation for the volume, right? We let V be the volume. The volume of the box. Okay. I'm not going to write the box. You know the meaning of the volume already. So thank you. And then identify the quantity you want to maximize depends on what other quantity? Depends on what other quantity? What quantity will determine the volume? At this point, volume is a unknown number, is a variable. If you cut off different size of the squares, the resulting volume is going to be different. And we also identify the volume, the quantity you want to maximize depends on what other quantity? Depends on what? Depends on the size of the corner squares. I'm going to tell you that. Okay. So try to understand that, okay? If the size of the corner squares is given, is determined, then the volume is determined, okay? If you change the size of the corner squares, and then the resulting volume is going to be different. So the volume depends on the size of the corner squares. What do we mean by the size of the corner squares? Everything is a square, the side length, okay? So just the x, my x, in step 1, okay? Just say let x be the side length. It's actually the side length of the corner squares. So to be cut. That's right. Yeah, to be cut. Okay. In this question, we just need the two variables. Okay. I want to repeat. It's kind of so important now. Okay. Identify the quantity you want to maximize. In this particular case, you want to maximize. In general, identify the quantity you want to optimize. Okay. And then you want to identify the quantity you want to optimize depends on what other quantity. Okay. That's step 2. So we're done step 2. And then in step 3, we make a list of relations. In general, we make at this point we make as many relations as possible. Okay. In this particular case, we have only 2 quantities. One quantity is the volume of the resulting box you want to maximize, and then the other quantity is x. You guys are smart. So anybody want to tell me how to relate the 2 quantities? I know it's a little bit too quick to ask you that, but you guys are smart. Anybody want to tell me the volume of the resulting box, how to write v in terms of x? The base of the resulting box, I will guide you to there, okay? The base of the resulting box is the dotted square, right? The base of the resulting box is the dotted square, and then the height of the resulting box is x. You just imagine you fold up the 4 portions, you make up the volume. I mean, you make the box. I'm looking for the volume of the box. How do you want to tell me the volume of the box, please? Okay, so just tell me how long is that? So did you see what I drew in there? So how long is that length? This is going to be 12 minus 2x. So that's 12 minus 2x. So it is good. Okay. The side length of the base is going to be 12 minus 2x. And then the area of the base is going to be, I think Harrison, you forgot a square. X times 12 minus 2x, the whole thing squared. The base of the box is a square. It's a square. So that makes sense. It's 12 minus 2x, the whole thing squared. This portion, the underlined portion, is the area of the base. And then after folding up the box, the height is going to be x. So that makes sense? Try to understand that, okay? It's easy. So just you have a box, something like this. Okay. I'm not good at drawing these things. And then the base is a square. The square has the length of 12 minus 2x, you told me, right? So the area of the base is 12 minus 2x, the whole thing squared. And then the height is x, right? It's kind of the formula for computing the volume of a rectangular prism. I think that's how you call it in high school. It's actually the volume of the box. Okay. Very shortly, the problem is going to be converted to a math problem. Okay. But we are not done yet. In the future, I really want to divide this step into many steps. At least 2 extra steps. Now you look at step number 4. Okay, you identify the dependent variable for which the maximum value is to be found. So that's the meaning. I'm translating the meaning. Okay, and also identify the independent variable upon which it depends. It's x. So we have done that. And then write the volume, the dependent variable, as a function of the independent variable. We have done that. We write v as a function of x. We write the volume as a function of the side length of the corner squares, right? So we have done that already. For this type of the questions, there's an additional step. So do not forget to identify the domain of the function. By that I do not mean identify the domain of that function mathematically. I mean using the real life problem, using the given problem to identify what is the largest possible value of x and what is the smallest possible value of x, using the real problem, using the word problem. Okay, now think x is the size, x is the side length of the corner squares, right? You have 4 corner squares. X is the side length of the corner squares. Now I'm trying to identify the domain of the function. By that we mean we are trying to identify the smallest possible value of x and the largest possible value of x. We are going to figure out, so something like this: x is greater than or equal to what number, or greater than what number. Okay, and less than what number. So just try to answer my question. Okay, anybody want to tell me the smallest possible value of x? X is the side length of the corner squares. What is the smallest possible value of x? So maybe my question is not proper, but so does that make sense? X can be as tiny as possible. X can be any number greater than 0. Yeah, so 6 is right actually. 6 is from 0 to 6 is right. Absolutely. Okay. And then using the real problem, you identify the largest possible value of x. You have to cut off the 4 corners, right? So does that make sense? Does it make sense x cannot be more than 6? I mean, x has to be less than 6 so that you can cut off a corner. Now let's say x can be 5.9 as long as x is very close to 6. A number very close to 6 is possible to cut off the 4 corners, right? So we are trying to say x can be any number greater than 0 and less than 6. You could use the interval notation, or you could use the inequality notation at the same time. Okay. So how about we just use the interval notations like Harrison told me. Okay. And then you say something like the function is defined on the open interval from 0 to 6. So you could write something like x is in the open interval from 0 to 6. So did I mention this notation before? I think I did, right? It means x is in that interval. Okay, x is any number in between 0 and 6. That's what I meant by finding the domain of the function. For this type of the problem, it's super important to include that step. I want to repeat again, it's super important to identify the domain of the function. So do you see now the problem is converted to a math problem we did the last time? Now the problem is converted to a problem, so let's do it carefully, it's converted to a problem of maximizing v, the function v, okay, on the interval from 0 to 6. Or alternatively, we can say find the maximum, absolute maximum of the function v when x is on that interval. Okay. After this step, so because in the question we only need the two variables, so we have combined the two steps, step 3 and step 4. So later on, we're going to see a question for which you have to divide 3 and 4 into two steps. In general, in step 3, you get as many relations as possible, so there could be more than one relation. And then you identify the quantity you want to optimize, and then you write that quantity, the quantity you want to maximize, as a function of only one variable. Okay, so later on, so we're going to see a question like that. But now I hope you can see we're ready to move on to use the knowledge we learned last time. At this point, we can write v as v of x. So because v depends only on x, so that makes sense. Again, at this point, the problem is converted to the problem we have seen last time. Okay. But in order it's easier to get to follow the 4 steps we learned last time, it's probably easier if we rewrite the function to some different form. Okay. I'm trying to say, in order to differentiate the function and get the critical numbers and so on, we'd better rewrite the function to some nicer form. Okay. You multiply out, you're going to get I'm going to do that in 2 steps, okay, so that I'm not running too fast. 12 squared, you have 144 minus, I think you have 48x. I was trying to use the formula like a minus b the whole thing squared equals a squared minus 2ab and then plus b squared. You just treat a as 12, okay. You just treat a to be 12, you treat b to be 2x, you have the form of a minus b the whole thing squared, right? 144 minus 48x and then plus 4x squared and then times x, right? So you have 144 times x and then minus 48x squared and then plus 4x cubed. The same function, again the function is treated as a function defined on the closed interval from 0 to 6. Okay. I want to repeat, after you understand the problem and getting the relations, the problem is converted to the problem of finding the absolute maximum of v of x when x is on that interval. Now we are going to follow the steps we learned last time to deal with this. I'm going to use A, B, C, D to denote the sub-steps we learned last time. Okay. Now in step A, we differentiate the function. So keep in mind we're using v to denote the function, so do not always use f of x. Okay. So this time we differentiate the function v of x. Okay. So the derivative is simple, right? So we have 144 minus, so now let's say 96 x, right, and then plus 12x squared in substep A, we differentiate the function. I believe you can recall that. You just did that for the assignment, right? And then in little step B, we get the critical numbers. Again, the critical numbers are the possible locations of local maximum and local minimum. By definition, the critical numbers are the values of x at which the derivative is 0 or dne, right? So in this particular case, the derivative is defined at all the real numbers. We just have to find at what x values the derivative is equal to 0, right? We're trying to get the critical numbers. We let the derivative be 0. So this means we have 144 minus 96x, right? And then plus 12x squared is equal to 0. Probably we did this last time. So did we? I can kind of remember this. Okay. Now I'm going to divide two sides of the equation by the constant, by the non-zero constant of 12. Okay. And then you have x squared minus 8x, right? And then plus 12. So you let me know if you see anything wrong. Okay. Is equal to 0. 96 divided by 12 is 8. Is that right? And then to get the critical numbers, we factor the equation. Okay. I believe we're going to have x minus 2 and then times x minus 6. So equals 0. In this question, it looks like we're going to have two critical numbers. Okay. I mean the solution to the equation, we have two solutions. One solution is x value of 2, the other solution is x value of 6. But one of the two numbers is not a critical number. So do you want to recall the details? Which solution is not a critical number? We're treating this function as a function defined on the closed interval from 0 to 6, which means 6 cannot be treated as a critical number, so because 6 is not on the interval. So that makes sense? Sure. Thank you. So we have only one critical number. Okay. So x value of 2 is the only critical number. You see the problem is converted to the problem we did last time. Okay. It's even the same problem we did last time. So do you want to recall what we do next? Now x value of 2 is a possible location. So we have only one critical number. Now let's recall the critical number is a possible location of the absolute maximum. Okay. Now to confirm that, in general we use a table. Okay. The next step is step C. Okay. Step C. Again, the interval is an open interval. At least it's not closed. Whenever the interval is not closed, then we use a table to confirm. In this particular case, 2 is indeed the location of the absolute maximum. Okay. Now let's recall how to form the table. To form the table, you think the interval is from 0 to 6, right? You think the critical value of 2 divides the interval into how many subintervals? We did this last time, so I can go over a little quicker, I guess, right? 2, I mean the critical number of 2 divides the interval from 0 to 6 into 2 subintervals, okay? From 0 to 2, and then the other subinterval is from 2 to 6, right? So that's how you get the first row. Okay. And then the second row, I mean the row title, you always label the second row using the same thing. It's the derivative of the function. You see, I was trying to write f, but in the question you have to use v, right? Because we are talking about v, you write the derivative of v, okay? And then the row title of the last row is v of x. So basically we are trying to use the derivative. I mean, in general, we are trying to use the signs of the derivative, positive or negative, to determine the property of the function, increasing and decreasing. From that, we can determine, we can check, we can verify if 2 is indeed the location of the absolute maximum or minimum. Okay, so the table is kind of in that form. Okay, and then in these two cells, you look at the mouse cursor. In these two cells, we're looking for the signs. We're looking for the derivative on the interval from 0 to 2 and on the interval from 2 to 6 is positive or negative. Okay, and then we're going to use the signs to denote, to determine if the function is increasing and decreasing and so on. Okay. Again, we mentioned last time, it's always safe. It's always safe to use the check numbers, the test point. It's always safe to use the test point to determine. Can you still hear me? Something was wrong with Teams. Can somebody confirm you can hear me? Sure, thank you. Cool. I think somebody was trying to call me. They just had a final exam. People are trying to claim marks. Okay, it's always safe to use the test numbers to determine the signs, right? It's a question we did last time. I'm not going over this in very detail. Okay. So, but you could use a test number of 1, and then you plug 1 into the derivative. We are looking for the sign. I believe the value of the derivative at 1 is going to be a positive number. So check your notes. So we did the last time. Okay, it's going to be a positive number. Okay, and likewise, you could use a test number of 3 on the interval from 2 to 6 to evaluate the derivative of the function at 3. So because 3 can be treated as a test number from 2 to 6. I believe that value is negative. We did last time. Okay. We mentioned last time it's always possible to use the test numbers to determine the sign. I mean, if the derivative at any test number from 0 to 2 is positive, then the derivative is positive at any number from 0 to 2. You could use any number to check. Okay. And likewise, the derivative of the function is always negative on the interval from 2 to 6. We mentioned the last time. We even mentioned y probably. Okay. So actually, why this is true is IVT. It's the intermediate value theorem. Okay. I think somebody was trying to call me. I saw a message, no internet, or whatever. The message is gone. I believe you can hear me now. Okay. Okay, and then after this, we can the derivative on the interval from 0 to 2 is positive. It means the function is increasing on that interval from 0 to 2. Right? You use a notation like that to denote the function is increasing, and likewise, the function is decreasing on the interval from 2 to 6. I want to repeat, the function is increasing on the interval to the left of 2. The function is decreasing on some interval to the right of 2. This is true for any x value on the interval from 0 to 2 and for any x value from 2 to 6. So 2 has to be the location of the absolute maximum. We mentioned that last time. You can imagine the graph. So to the left of 2 the function is increasing, to the right of 2 the function is decreasing. Okay. So 2 has to be the location of the absolute maximum. And then in step D you can confirm that. Okay, so the function v of x has its absolute maximum at x value of 2. Now you look at the question. So in the question, we're looking for the size of the corner squares. I mean, we're just looking for what value of x the volume of the box is maximum. We're not looking for the size. I mean, we're not looking for the largest volume. We're not looking for the value of the largest volume. So do you know what I mean? It's kind of, we're only looking for the location. We're not looking for the value. Okay. What I'm trying to say is that if you are not asked to compute the volume, you do not need to compute the volume. You just answer the volume is the largest absolute maximum when x value is 2. Okay. And then you are ready to answer the question. Okay, now let's go back to the step procedures. I think we have done step 5. Step 5 is actually a long step involving 4 sub-steps. Okay. Using the 4 sub-steps we learned last time. Eventually, it's a word problem. It's always the case for any word problem. The last thing you do is to answer question in words. Okay. Now we are going to answer the question in words. Okay. I don't remember the step number. Now step 6. I think it's step 6. In step 6, we answer question in words. Okay. To answer question, you look at the question. We're looking for what size of the corner squares should be cut so that the resulting box has the largest volume. You just answer the question. Okay. Corner squares of size so maybe 2 by 2 square inches. When you're talking about the area, it has to be in square inches, right? Of size 2 by 2 square inches should be cut. To produce the box of the largest volume, right? The maximum. I think you can do the last step. It's way better than me. Okay. So just look at the question and try to answer the question. Again, now let's go back to the real problem. The real problem is we want to decide the size of the corner squares, so to be cut so that the resulting box has the largest volume. You can imagine this kind of things is useful in real life. Probably next question you are going to see a more convincing stuff in real life we can work on. Okay. Any questions about this? To summarize a little bit. In step 1, you draw a sketch. In step 2, you introduce the variables. Okay. Identify the quantity for which you are given. Identify the quantity for which you are maximizing or minimizing. Okay. And then you identify the quantity depends on what other quantity. Eventually, you write v as a function of only one other as a function of only one other variable. I mean, okay. And then very importantly, identify the domain of the function using the real problem. Okay. And then use the stuff we learned last time to find the absolute maximum or absolute minimum of the function on some interval. Okay. Finally, answer the question in words. Try to understand the problem. In step 1, I think you can remember that. We draw a sketch. A farmer has 240 meters of fencing. You know the total fencing. And then he wants to make a rectangular pen. It's a big pen, right? Something like this. I cannot remember the question. You read the question, okay? The pen is to have one internal fencing that run parallel to the end fences, so that you have two sections. Okay. The pen has two sections. One larger section for large pigs, right? One smaller section for smaller pigs. Okay. So something like this. Actually, you have only one condition. The condition is that actually you have many conditions. You know the total fencing. You have one other condition if you read the question. Okay, the condition is that the length of the larger section is twice the length of the smaller section. Okay. If you look at the mouse cursor, that's the larger section. The length of the larger section is twice as long as the length of the smaller section. So that is the problem. You know the total fencing. The total fencing is 240 meters. Okay. And then you want the pig pen. I mean the two sections. The area is the largest. Okay. So that is the problem. If you want me to make more comments, actually the pig pen can be something like this, as long as his lot is long enough. So it could be something like this. The total fencing is 240 meters, and then the length of the larger section is twice the length of the smaller section. It could be very long that way, right? It could be very long that way, horizontally. So can I say horizontally? And then I believe you can imagine the area is not going to be the largest. So it's because the two sections is too narrow. Can I say narrow? Right. Or alternatively, he could make the fencing very long that way, vertically, that way. You can make all the conditions satisfied, right? The total fencing 240 meters. The length of the smaller section is twice. It's half of the length of the larger section, and so on, right? Again, the area is not going to be the largest. I believe you can imagine, right? Now the question is, we are looking for the size of the two rectangles so that the area is the largest. When he do the fencing, when he does the fencing, he wants the area to be the largest, right? So it can hold more pigs. That makes sense? So draw a sketch. Okay, in step 2 we introduce the variables. Anybody want to tell me what quantity you want to maximize? For what is the quantity we want to maximize in this particular case? We are looking for the dimension to produce the largest area, the area, okay, the total area actually, okay. So we let A be the total area. It's kind of the standard notation, right? We let A be the area, be the total area. of the two sections. I'm not going to write the two sections. You know the meaning already. And then we're going to see the total area depends on what? What are the variables? Okay. I will show you how to choose the other variable. Okay. So can I use actually the other two variables are the side length. So maybe the length and the width of the rectangles. You know the area is dependent on the length and the width, right? So can I use x to denote the length of the smaller section? And then the length of the larger section is going to be 2x. So because we have a requirement that the length of the larger section is twice the length of the smaller section, right? For this question, it's easier if we introduce one other variable. I mean, in addition to x, we want to introduce one other variable. So can I use y to denote width? It's kind of the width, but I'm not going to introduce the term. I'm going to use y to denote the width of the rectangle. Okay, so both sections. So can I just write let x and y be as shown? If you really want to write everything in words, you could say something like let x be the length of the smaller section, and let y be the width of the rectangles. Okay, I think you know the meaning already. Okay. So we're done step 2. Again, in step 2, the most important thing is to identify the quantity to be optimized. In this case, you identify the quantity so to be maximized, right? We want to maximize the area. Does that make sense? And then the area is dependent on the width and the length. At this point, you could introduce as many other variables as possible. Okay. Now, in step 3, we get as many relations as possible. Okay. How do you want to write a in terms of x and y? Again, in step 3, we write as many relations as possible. We get as many relations as possible. How a is the total area. Anybody want to tell me how to write a in terms of x and y? A is the total area. So try something, please. You know that. The area of a rectangle is the length times width. So what is the length? What is the width? Anybody? So try something, please. How do you write a in terms of x and y? X and y, please, in terms of x and y. Three x, right? A is the total area. A is the total area. You have 1x here, 2x here. Can I label some corner points? I mean, can I label the rectangle using some points? I want to call this point A. I want to call this point B. So maybe, so temporarily I'm going. So what is the length of AB? AB is 3x, right? And then the width is y. So that makes sense. A is 3x and then times y. So that's the area. Okay, so that's the area. And then what is the meaning of total fencing of 240 meters? You have a total fencing of 240 meters. 240 meters, the total fencing of 240 meters will give you another relation between the variables. How to interpret the meaning of 240 meters? It's the perimeter. I mean how to write 240 in terms of x and y. Okay, you have x there, you have x there, you have a 2x here, right? It's a rectangle. And then you have y here, you have y here, you have y here, right? Actually, altogether you have how many x's? 6x, right? So that makes sense. You have 6x, 3x on top, 3x at the bottom, and then you have 3y's, right? 6x and then plus 3y equals 240. So that makes sense. 240 meters of fencing is that, right? Okay, now you look at step 3. In step 3, we get as many relations as possible. Okay. In step 3, we get as many relations as possible. It's easy. It's just a rectangle. Total fencing is 240 meters, right? He used the total fencing of 240 meters to make the big pen. Okay. And then the area is the length times width, right? So we're done step 3. Eventually in step 4, we want to write, I think I can squeeze step 4 in here so that you can see everything on this screen. Okay. In step 4, we want to write A, the quantity to be maximized in this case, as a function of only one variable. In this particular case, so probably we can write A as a function of only x. I want to repeat, the next thing we do is to write A as a function of only x. To achieve that, we can solve the second equation for y. I'm going to label the two equations. I will call that equation 1. I will call that the equation 2. Okay. In step 4, again in step 4, we want to write A as a function of only one variable. Okay. So maybe from 2, we have, I told you before, it's permissible to divide two sides of the equation by a constant number, by a non-zero constant of 3. So in this case, okay, we have 2x and then plus y. We divide equation 2 by 3, okay, equals 80, right? And then we can solve this equation for y. By that we mean we want to write y in terms of x. So y is equal to 80 minus 2x. Okay. So just try to follow me. Why do we do that? We want to plug y value, y equals 80 minus 2x into equation 1. So we can write A as a function of only one variable, x. Okay. You're going to see what's going on. Okay. I'm going to call this one equation 3. Okay. Now we plug equation 3 into equation 1. We have A equals 3x and then minus y. I'm going to replace y with 80 minus 2x. At this point, you see A is represented as a function of only x. That's what I wanted. Now let's go back to the step procedures. Okay, we want to write the dependent variable A as a function of only one variable x. That's what I wanted. Okay. A is the area. Okay. The area now is a function of only one variable. At this point, I can replace A with A of x. I hope I'm not running too fast, but you know what's going on? I can write A as A of x because now I can treat A as a function of only one variable x. So do not stop here. Super importantly, you need to identify the largest possible value of x and the smallest possible value of x. By that we mean you identify the domain of the question from the real problem. Anybody want to tell me the smallest possible value of x? So this time I'm going to use the inequality. Okay, what is the smallest possible value of x? We'll make pigpens. What is the smallest possible value of x? Or better, anybody can figure out the interval on which x lives in. X can be any number greater than 0. Anybody want to tell me the largest possible value of x? The largest possible value of x? You guys are smart. Anybody want to tell me the largest possible value of x? Forty is right. 40 is right. 40 is right. Okay. If you can see 40, then you really know what's going on already. Okay. For people who do not see 40, for people who do not see 40, I'll give you some hint. Okay. The smallest possible value of y will give you the largest possible value of x. What is the smallest possible value of y? What is the smallest possible value of y? You remember the total fencing is 240, okay? And the smallest possible value of y is kind of 0. Actually, it cannot be 0, but it can be any number very close to 0, right? We just use y value of 0 to determine the value of x. That will give you the largest possible value of x. So that makes sense? I will show you what's going on here. On scratch paper, you do the following. You use y value of 0 to solve the equation 6x equals 240. And then you solve the equation, right? You divide two sides of the equation by 6. You have x value of 40. Right. Again, I want to repeat. The smallest possible value of y will give you the largest possible value of x. We're trying in here, when determining the domain of the function, we're trying to determine the largest possible value of x and the smallest possible value of x. The smallest possible value of x is simple to identify, 0, right? And then the largest possible value of x is determined by the smallest possible value of y, okay, which is 40. At this point, the problem is converted to a mathematical problem. Okay, it's converted to the problem of finding the maximum value of a when x is from 0 to 40. Right. Any questions so far? The first step is super important. You need to understand the problem by drawing a sketch, and then introduce the variables. In this particular case, it's kind of necessary to introduce both x and y. Okay, and then in step 3, get as many relations as possible. And then the target of step 4 is to write a, the area, the quantity, so to be maximized as a function of only one variable x. Okay. More importantly, identify the domain of the function. Okay. We're done step 4. Now we're on step 5. I need this for step 5. So the problem is converted to a mathematical problem already, finding the maximum value of the function a when x is from 0 to 40. Okay. In order it's easier to get the critical numbers, we write the function in some nicer form. A of x is equal to, I just trying to multiply them out. Okay. 240. 3 times 80 is 240. 240x, right, minus 6x squared. Simple, right? It's actually a quadratic function. And then the domain of the function is treated x lives on the interval from 0 to 40. Okay. Now we follow the steps we did last time. Okay. Can I write a little step A again? In little step A, we differentiate the function. So we have 240 minus 12x. So differentiate the function, right? And then in step B, we get the critical numbers by solving the equation. The derivative of the function is equal to 0. Okay. So we have 240 minus 12x, so equals 0. This one is simple, right? I believe x is 20. If you want me to include more steps, so 240 minus is equal to 12 times x, and then you divide two sides of the equation by 12. You have x value of 20. In meters, in this particular case, we have only one critical number, right? Okay. And then in step C, the critical number is only the possible location of the absolute maximum in this particular case. To confirm x value of 20 is indeed the location of the maximum. I'm talking about the math problem. Okay, you need to use a table to confirm. So because the interval is an open interval, you have to form a table. Actually, okay, I forgot to mention the second derivative test. We're going to mention that later, but at this point, so the following is kind of called the first derivative test. Okay, you just remember you need a table to confirm that 20 is indeed the location of the absolute maximum. Form a table something like this. The interval is the open interval from 0 to 40, and the critical number is 20. 20 will divide the interval from 0 to 40 into two subintervals, right? One subinterval is from 0 to 20. The other subinterval is from 20 to 40. I'm using the interval notation. It's also okay to use the inequality notation. Okay, and so here you write the derivative of the function. Okay, the derivative of the function a, so which is 240 minus 12x, right? And then the title of the next row is the function a of x. The following is the stuff we did last time. I'm not going to talk about that in more detail, but I just want to mention how to choose the test numbers. Okay, choose a number from 0 to 20, any number. Okay, so probably you want to use a simple number, so like 10. Okay, as a test number, and then you evaluate the derivative at 10. The derivative at 10. Okay, I'm trying to say you evaluate the derivative of the function at 10. You do not need the value, you need the sign, right? So you have 240. You look at this line, the derivative. Okay, you have 240 minus 12 and then times 10, right? Whatever number you get, I believe it's going to be a positive number. Okay, so you put a positive sign here. Okay, and likewise you can use 30 as a test number, because 30 is a number on that interval. Okay, and then you evaluate the derivative as 30. I'm pretty sure you are going to have a negative number. Use any test numbers on the intervals, on the subintervals, to determine the signs, and then use the signs of the derivative to determine the function is increasing or decreasing. The derivative is positive on the interval from 0 to 20. It means the given function the original function a of x is increasing on that interval, right? And likewise, the function is decreasing on the interval from 20 to 40. This is the table confirming that 20 is indeed the location of the absolute maximum. Right? So because the value of the function at any other number is smaller than the value of the function at 20 for sure. Okay. Answer the question. Okay. In step D, answer the question mathematically. Okay. Answer the questions mathematically. So what do you say? Okay. So the given function a of x is maximized. Again, you are not asked for the area, for the value of the area. You just answer the location. Okay. So the function using the table a of x is maximized. Okay. When x value is equal to 20. Okay. Meters, in meters, of course. All right. That's 4 sub-steps in step 5. And then eventually you need to answer question in words. Okay, so we are looking for the dimensions that produce the pen of the maximum total area. Okay. Finally, you answer question in words. So can I skip that? This is a question on in the course manual. If you want to check the answers in details, you could check the course manual. Okay, but now I'm going to skip that. Any questions so far? Any questions so far? So maybe I'm going to summarize again. Okay, in step A you draw a sketch. In step 1 you draw a sketch. Understand the problem. Like the meaning of 240 meters of fencing. Like the length of the larger section is twice the length of the smaller section, right? And then you introduce the variables, identify the quantity you want to maximize, the most important thing. Okay, and then you identify A depends on what. You could introduce as many variables as needed. Okay. In this particular case, the area depends on the length and the width, right? You just introduce x and y, use x and y to denote the length and the width. So because the area is the length times width, right? And then in step 3, you get as many relations as possible. A in terms of the length and the width is 3x and then times y. So do not forget you have a condition of 240 meters of fencing and so on. Okay, using that condition, you can write A as a function of only x. It's also okay to write x as a function of only y. It's also possible. Okay, I'm trying to say to write A as a function of only one variable, the way is not unique. Okay, as long as you can achieve that, identify the smallest possible value of x, the largest possible value of x. Okay, identify the domain of the function. Okay, and then you can convert the problem to a mathematical problem. After that, you follow the 4 steps we learned last time to confirm the critical value. The critical number is indeed the location of the absolute maximum. So in this case, okay, and then you answer the question in words. That's everything. Okay. Any questions? If you don't, then we move on to the next question. The next question I want to work on is question number 2. So we did question number 2. Actually, question number 1. Sorry, question number 1. You can see for many questions you need to use some geometry or some other things. But so don't worry too much. So before the final exam, I will give you hint on what formulas you need to memorize if it's close book. In question 1, you need the volume of a cylinder, the surface area of a cylinder. Okay. In step 1, we draw a sketch. You want to make a cylinder. You know the volume. The volume is 1.5 liters. Okay. And then you're trying to determine the dimension of the cylinder that will minimize the material. Okay. So this time we're going to see a minimization problem. Okay. In step 1, you draw a sketch. You just have a cylinder. Illustration only. Okay. Cylinder. Right. So this time you have a closed cylinder. So by that we mean, so there's a top cover, so there's a bottom cover, of course. So we're done step 1. Okay. The only condition you know is that you know the volume. You want the cylinder, the can, to hold 1.5 liters of liquid. Okay, that's the only condition. And then you are looking for the dimension of the cylinder. By that we mean we are looking for the height, and we are looking for the base radius, so that the can has the smallest possible surface area. Minimize the material. It means to minimize surface area, right? So we're done step 1. We're done step 1. Okay. In step 2, the most important question is identify the quantity to be optimized. Identify the quantity so to be minimized in this particular case. What do we want to minimize? Anybody? What do we want to minimize, please? What is the quantity to be minimized? Material is right. So what's the meaning of the material? Surface area. Yeah, that's right. Surface area. Okay. So thank you. We're going to use the standard notation for the areas. Okay. So we let A be the surface area. Of the cylinder. Okay, just write surface area. We're talking about the cylinder. Okay. So, but remember, we're talking about a closed cylinder. So there's a top, so there's a bottom. Okay. At this point, A is the surface area of the cylinder. You can check the formula online right now, or you can. If it's better if you could remember what is the formula for the area of the cylinder. I'm trying to say the area of the surface area of the cylinder depends on what? I believe you can imagine. Later on I will tell you the formula, but the formula is in terms of the base radius and the height. So that makes sense. The base radius, we're going to use r to denote the base radius, and then we're going to use h to denote height. I hope it's not too messy, but you know the meaning of the base radius and the meaning of the height, right? I will write it down. Okay. I'm trying to say the surface area depends on the base radius and the height. So we're going to let r be the base radius, and we're going to let h be the height. Everything is relevant to the cylinder. Okay. Again, the most important variable you need to introduce is the quantity to be minimized or maximized. In this particular case, we want to minimize surface area, right? And then you have a formula for computing the surface area. It's in terms of the base radius and the height. So very shortly, you're going to see that. Yeah, that's why I need to introduce the base radius. I need to introduce the height. Okay. Does that make sense? Now step 3. In step 3, we get as many relations as possible. Okay. Anybody want to tell me the formula for computing the surface area of a cylinder? We use A to denote surface area, right? Or if you do not remember, it doesn't matter. So there's a top, so there's a bottom, right? The area of a circle is pi r squared. So that makes sense. The area of a circle is pi r squared. At least you should know this. So there's a top, so there's a bottom. So you have two of these. You have two of these, right? And then what is the surrounding? I mean, we have seen the top is pi r squared. We have seen the bottom is pi r squared. What is the surrounding bit? The shell part. You just imagine you cut off the cylinder. Cut off the cylinder, you have a rectangle. So probably so that's how you were told. I'm going to tell you the formula, okay? It's 2 pi r h. It's 2 pi r. 2 pi r part is the circumference of the circle, and then you times multiply that by the height. You have the surrounding bit of the cylinder, which people call it the shell part. I said shell. Okay, so that's the formula. The bottom line is, try to remember that. You learned that in junior high school. Okay. The bottom line is the surface area in terms of the base radius and the height is represented by that. Okay. You see at this point the surface area is dependent on two things: the base radius and the height of the cylinder, right? That's one relation. Of course, eventually we want to write A in terms of only one of R or H. You have one other condition we haven't used yet. How do you interpret this 1.5? This 1.5 is the volume, right? 1.5 liters. Liters is actually cube decimeters. Probably many of you guys are in chemistry now, are doing chemistry right now, or not too long ago. You know the conversion, right? Liters is cube decimeters. Okay. And then, how do you interpret 1.5 liters? It's the volume, right? The volume of 1.5, whatever unit, so temporarily you do not have to care. So this is the volume, 1.5. What is the volume of a cylinder? The volume of 1.5 is equal to base radius, the base area, then times height. Base area is pi r squared, and then times height. Okay. If I'm telling you that, I believe you can remember. Okay. It's just a long time ago. Probably you learned that a long time ago. You need to recall the thing. Okay. But again, the first formula is the formula for computing the surface area of the cylinder. The second formula is for computing the volume of the cylinder. Okay. 1.5 is in liters. Now I want to make R and H, the radius and the height, in decimeters. Okay. In step 3, we have two relations, right? Okay. Now the thing in step 4, if you can recall, I will show you step 4 again. Okay. In step 4, the basic idea is to write the quantity to be minimized, in this particular case, the surface area, as a function of only one of R or H, whichever is simpler. I will tell you what's going on, okay? Because in equation 2, it's easier to solve the equation for H. By that I mean it's easier if we write H in terms of R. So because we do not have to take the square root, that's how we can write A as a function of only one variable R. I will show you the details. Okay. Okay. Probably so before I will write that in step 4. It doesn't matter. Okay. So maybe from equation 2, we have H is equal to, so basically in step 4, our target is to write A as a function of only one of R or H. Okay. From equation 2, we solve the equation for H. So you can see H is equal to 1.5 over pi R squared. I'm going to call that 3. Okay. Now from equation 3, actually we plug 3 into equation 1. Okay, I just cross that out. Now we're going to plug equation 3 into equation 1. Now watch. Again, in this step, we want to write A, the surface area, as a function of only R or H. Okay, you're going to see what's going on. The surface area now is equal to 2 pi R squared, and then plus 2 pi R H. Now I can replace H with I do not want to use X here. Can use a dot to denote the multiplication. And 2 pi R H, I'm going to replace H with 1.5 over pi R squared. I believe you see what's going on, right? You see, after doing that, A is a function of only one variable R. I mean, A is in terms of R only. H is gone. So do you know what I mean? At this point, I can write A of R. So because A is dependent only on R now. Later on, we are going to identify the smallest possible value of R, the largest possible value of R, of course. Okay. But before that, I'm going to simplify a little bit. Okay. A of R is equal to 2 pi R squared, and then plus, you see, you can cancel the AR, cancel the pi from the top and the bottom. I think the second term, after simplifying the second term, you have 3. 3 is coming from 1.5 times 2. Okay, 3 over, I think 3 over R only. Any questions about this? You see, in step 4, our target is to write the quantity to be minimized as a function of only one of R and H. In this particular case, A can be written as a function of only R, the base radius now. Okay. Anybody can recall the next thing you need to do? We're not done step 4 yet. The most important thing, one of the important thing we need to do in step 4, we are going to identify the domain of A of R. we are going to identify the largest possible value of r, the smallest possible value of r. But anybody want to tell me the smallest possible value of r and the largest possible value of r, please? You just use the condition. The only condition you want to satisfy is that the volume is 1.5 liters, a fixed volume. And then under that condition, you identify what is the largest possible of the base radius, what is the smallest possible value of the base radius. Anybody want to try? What is the largest possible value of the base radius? What is the smallest possible value of the base radius? Actually, the base radius can be any small, can be as small as possible. You want the volume to be 1.5 liters. If the base radius is tiny, you just make the cylinder very tall, so that you want the volume to be 1.5 liters. It's possible, right? For any small value of r, for any small value of the base radius, you just make the height very tall, so you can make the volume 1.5 liters. I'm trying to say r can be as small as possible. R can be any number. R can be any positive number. Okay. Anybody want to imagine the largest possible value of r? Actually, r can be as large as possible as well. Okay. You just imagine you want the base radius so to be gigantic, any large. So now let's say 100 meters, 10,000 meters. If you want the volume to be 1.5, you just make the height very tiny. So that makes sense? You just make the height very tiny. Okay. I'm trying to say r can be any number in between 0 and infinity. Can I use infinity? Or you could use, or it's better to use the interval notation. So you could say r can be any number in between 0 and infinity. Okay. So that makes sense? I'm trying to say the only condition is that the volume is 1.5 liters. To achieve that, you can make the base radius as small as possible or as large as possible. So r can be any positive number. Okay. So do you see the problem is converted to a mathematical problem now? I'm going to copy these two lines now. Okay. In step 5, we do the math part. Okay. Now we are on step 5. In step 5, the problem is converted to the problem of maximizing A of r when r is any positive number. Okay, in sub-step A, we differentiate the function. Okay, the derivative of the function with respect to r. So do not use f, do not use x. Now the variable is r. The function notation is a. Okay, I think we're going to have 4 pi r, right? And then minus the derivative of 1 over r with respect to r is negative 1 over r squared. You just use that and treat 3 as a constant factor. So you have minus 3 times r squared. That is the derivative, right? In step A, in sub-step A, so differentiate the function. In sub-step B, we find the critical numbers, right? Again, the critical numbers are the values of r at which the derivative is equal to 0. We set the derivative to be 0, and then we have 4 pi r minus 3 over r squared is equal to 0. Okay. I think we have seen how to solve the equation like that. So just so this time the numbers are going to be a little bit weird. Okay. I will solve it for you. Okay. Leave the term 4 pi r on the left hand side, and then on the right hand side you have 3 over r squared, and then cross multiply, kind of isolate r. Okay. So we have r cubed equals 3 over 4 pi. So do you see what's going on? Cross multiply. If you want me to write the whole thing in 2 steps, so we have something like cross multiply. Okay, 4 pi r cubed equals 3, and so we have r cubed equals 3 over 4 pi, and then we have r equals cube root of 3 over 4 pi. Okay. I need your help. So anybody want to tell me this number in decimal? You could leave this number like that. So, but very shortly, I'm going to show you something. 0.62. Sure, thank you. We round the number to two decimal places. So kind of okay. This is approximated by the 0.62. Okay. That's kind of the critical number. Okay. So write down step 2. Write down step B. Okay. We kind of found the critical number. And then in step C, we form a table to confirm is indeed the location of the absolute minimum, actually, right? The critical number divides the interval, the domain from 0 to infinity into 2 subintervals. One subinterval is from 0 to 0.62, and then the next subinterval is from 0.62 to infinity, right? We have two subintervals. The function notation now is a, right? We want to use the derivative of a to determine the signs, right? In these two cells, in that row, we are looking for the signs, and then we use the signs of the derivative to determine the function is increasing or decreasing, right? We mentioned before you can use test numbers. Now, for instance, you can use any number on that interval as a test number to determine the sign of the derivative on that interval. Okay. You could use the test number of 0.1, plug 0.1 into the derivative of the function, and then you look for the sign, right? I believe the sign here is negative, and the sign of the derivative on the interval from 0.62 to infinity is positive. So the function is decreasing on the interval from 0 to 0.62 and increasing on the interval from 0.62 to infinity. Okay. So that's okay. I'm not actually verifying. You could use any test number. I'm kind of run out of time. I'm going to make more comments. Okay. I want to make more comments. So because okay. Don't know what I mean. Okay. So we're done step C. Okay. Now using the table confirms 0.62 is indeed the location of the absolute minimum. Okay. And then mathematically you can say something like A of R, the surface area, so do not lose track of the meaning. A of R, the function, is minimized when the base radius of R is equal to 0.62. I told you if the volume is in liters, the base radius should be in decimeters. So because liters is cube decimeters, di for decimeters. Finally, answer the question in words. Okay. Now I believe we are on step 6. Answer the question in words. So just remember that number, okay? The base radius is equal to 0.6. After doing that, I need one other favor from you actually. So do you want to recall there's a relation between the base radius and the height? Now I'm trying to ask you, if the base radius, if R value is 0.62, what is the value of H using that formula? So please try to use that formula to compute H, the value of H. We need that number to answer the question. Just plug R value of 0.62 into that formula to compute H. You can keep on computing, and then I'm going to answer the question in words. Okay. To minimize the material or the surface area of the cylinder, okay, to minimize the material, the cylinder, the can, the cylindrical can is to have the base radius of, you told me it's 0.62 decimeters, right? And the height, I think we'd better figure out the height. The height of, now let's compute the height on this screen. So we have the height 1.5 over pi r squared. Pi times 0.62, the whole thing squared. I told you to compute this value. I believe all of you guys know this value, know how to compute at least. Okay. This value is actually 1.24. Plug the numbers in, you have 1.24 decimeters. Okay.